And our final talk is going to be Virtualizing LinkedIn's Pops Up via Northguard-Xinfra. And Wesley and Ku from LinkedIn will deliver this talk. Some FAQ common questions that we receive: are the talks being recorded? Yes, they're recorded and they will be posted to YouTube by LinkedIn Engineering channel. The meetup event site will also share the recording after the meetup. For remote participants, the questions will be posted using the Q&A tool at the bottom of the Zoom. And you can just use it anytime during the meeting. We will take the questions at the end. Presenters will answer the questions. Depending on the time, we may cover some of the remaining questions after all talks conclude. For in-person participants, you will just ask the questions after the talk, and we are going to pass the microphone for the persons to ask the questions. So if you're interested in presenting in our meetup, you can post a message on the meetup site. You can send a LinkedIn message to me, Adam Figenja, Gary Young, our co-host, Boris is another co-host, or Beckett. And you can also send email to any of the hosts of the event. With that, I'm going to pass it to our first speaker. Pete Goddard is the founder and CEO of Deephaven Data Labs. This is a spin-out from Walleye Capital, the hedge fund he founded. With 25 years of experience running businesses powered by real-time data, Pete is passionate about advancing the state of real-time data processing. He and the Deephaven team believes that while Apache Kafka has revolutionized data transport, the next step is a similarly transformative leap in driving insights and driving action from real-time data.
Thanks very much for that introduction. That was, I forgot that was going to lead all of this, so I much appreciate it. Let's see if we can plug in, and maybe we'll see a white screen pretty soon. All right, excellent. So as suggested, I'm Pete Goddard. I'm the founder and CEO of Deephaven Data Labs. I'm in from Minneapolis. It's a real pleasure to be with all of you. It's not that often that I get to be in a room with, a bunch of innovators that are really at the cutting edge of things, particularly at an interesting time like this. I'm here to talk to you about a new abstraction and some open source software that we make available around an idea called live Dataframes. I'm going to spend some time describing it to you and talking about some of how it works and how it came about. And then I'll show you some demonstration of some use cases that hopefully trigger your imagination, certainly leaving some time for some Q&A at the end. I thought of just opening an IDE and starting by writing code, but we're sitting here eating chicken wings and drinking Cokes, and it seems to make sense to, before we actually demonstrate the capabilities of the query engine that are quite unique and describe the software stack that goes along with it, to maybe ground all of us in some context, to tell a story about how this came about and really try and focus on the core idea of why this exists and the abstraction that it brings to bear. In particular, it's that abstraction that I'm really hoping to ground your imagination in, because we think it is something that can take real-time processing to many, many more use cases. And in a time of LLM agents reaching into real-time data, we think it really might be quite important. But maybe I'm getting ahead of myself. As a way of introduction, I studied engineering at the University of Illinois. I disappointed my parents by rejecting a job offer to go work in the satellite industry, and instead started out as a trader on the Chicago Mercantile Exchange floor. For the young people in the room, that picture on the right is indeed what it looked like. We wore funny coats and waved our hands at each other all day long in an effort to try and buy low and sell high. I only stayed on the floor for a year. I spent the next decade or so working for big banks, doing OTC and exotic options, culminating in a position managing a pretty big group of technologists, quants, and risk managers across a pretty big portfolio of derivatives. And so that means I enter the room probably a little differently than most of you. And that is, I really come into this room thinking that business is driven by software and technology, that it is fundamental to P&L. That's where I come from. That's my first bias. The second bias is that real-time data really matters, and not just the source data, but the processing, the derived data, the real-time applications and models, that they're really fundamental to business. And then the third is that many people, and today, frankly, hooks and agents all need access. A greater variety of them need access to that data because they have use cases, and to the extent that they can self-serve, this is really compelling. So as I'm talking to you, who I think are the people that live at the intersection of event streaming and use cases, and the people that rely on you and stand on your shoulders, I think you want to think of the software we're talking about is serving them quite directly. So my founding idea is that real-time data tech is increasingly important to business. We know this is true in the capital markets for 20 years, 25 years. It's increasingly so in many other industries, whether it be IoT or e-commerce or healthcare, industrial telemetry, data centers, and the like. Obviously, personalization, things like this. As suggested in the introduction, I put my money where my mouth is in regards to real-time data, founding Walleye Capital in 2005. It started out as one business and pivoted to another. And at that pivot, we needed a general purpose data system that was good at real-time data, was good at batch data, and that a lot of people can use. Nothing existed, so we rolled our own. We mutualized it, spinning it out a number of years ago, and have since open sourced it. And this idea is really important. Like, real-time data and real-time processing needs to be available to LLMs and lots of people. But that culminates in a critical abstraction. It's not just an idea. That abstraction is grounded in something fundamental. People love tables. People love ordered tables. They love structured tables, data frames. They just love them. Excel, SQL, Pandas, R, these are ubiquitous, powerful technologies, and they love them for good reason. They're intuitive, easy to learn, easy to use. The mental map is just sweet, right? And they're also comprised of the arrays and the vectors that are highly interoperable with so many libraries. And frankly, if you listen to Sam Altman talk, like, he always talks about, everything calling Python. So Python can pull into these data frame technologies very well. But the real key, and it's something we all take for granted in batch, is that the real key of data frames and SQL tables is that they're composable. It means that the end product of your query, the end product of your Panda script, is always something that can be used as the input to something else. And this is key to enterprise because it supports asynchronous development, and it future-proofs your technology because whatever, the work product that's been produced can just work. It's A16Z, I mean, we're in the land of it. It's A16Z that said composability is to software as compounding is to finance. So what we've done is we've taken this idea, this thing that people love, these data frames, and we've simply made them live. We made them live by tracking their changes incrementally. Think of every 10 milliseconds or every 100 milliseconds. You write a script or you use a SQL query or you write an application that sets up a graph. And the changes in the data frame simply flow through the graph and update all the nodes in the graph incrementally. We do this in a way that maintains the ordering of the data frame so that you can have that composability, and is highly performant, so it's column-oriented. So this can support countless data frames talking within a single process, but also over the wire to support complex use cases and scale. And this means that live data frames, this is what I'm trying to drive home in regards to contemplating this abstraction. Live data frames are sort of a generalization of stream processors, and they're good for lots of things. Certainly, they can do the streaming pipelines that many of you are probably addressing today in Flink, which is also an outstanding technology. But they are just natural for addressing batch and streaming together, to moving from one to the other, for marrying your Python or your LLM's Python to your real-time streams. and to supporting UIs, because many UIs and their plots are well served by viewports, which can naturally be backed server side by those data frames. So I'm going to, in just a couple of minutes, try and demo the software a bit. But I want you to understand the architecture as we're going in. It starts with a query engine called DeepHaven Core. This is all open source. I'll be using it in Python. You could use it server side in SQL or Java. And again, it's great at the table operations and time series you'd like, but I'll also show you bringing third-party libraries and user-defined functions to the data. On top of that, because you don't want to work only within one server, you need them to talk to each other and collaborate. We've written a wire protocol. We based it on Apache Arrow Flight. Many of you probably know Apache Arrow Flight is just a wire protocol that's built on top of gRPC. So now we've brought this idea of event streaming and the Kafka world to the gRPC world. Like, they're married, it works. And we do all this by just taking the deltas of those data frames and passing them on the wire. So again, you can have dozens, hundreds, thousands. One of our customers has a goal of hundreds of thousands of DeepHaven engines collaborating with each other in real time. On top of that, we layer client APIs, because of course you're going to have client applications in many different languages, and therefore you need to remotely control the server. You need to bidirectionally pass data, streaming and batch back and forth from the client to the server, and vice versa. And then, in the batch world, as you guys all know, there's this huge ecosystem of like BI tools and dashboards and things like that, but they don't work very well in real time. They just don't. They don't marry very well to Kafka. Invariably, you guys all take Kafka and marry it to Flink and then write it to an S3 bucket, and then a BI tool can use it. But that isn't the future. That's an artifact of limitations of technology of the past. So our users and our customers have asked us to develop a web framework around these real-time live data frames. So we've extended that into open source, and you'll find that it has a good grid, it has good plotting, it has great visualization capabilities. And then we've created a Python library that lays on top of that, so that you can create dashboards programmatically, describe your interfaces, customize things, sort of like you would with Streamlit or Dash if you're Python people, but do it in real time. They're highly interactive. And all of this we've delivered as open source software. You just have to go to DeepHaven or GitHub on DeepHaven, and you'll certainly find everything there. So now I'm going to transition to show you to see what live data frames can do. I have a few rules of the demo. One, I'm going to start or use, I think, primarily crypto data, only because it is publicly available streaming data that I can get here at LinkedIn with no problem. So it's not a political statement. It's also not, it may not marry to your use cases. So I hope you can understand. These are just Java and Python data types. You can do whatever you want with them. I'll be manipulating them with joins and aggregations and things that are familiar with you. I also encourage you, though there is a UI element to this, not to be dominated by the UI, because there's all the money in the world is made through headless applications, most of the money, not just people looking at screens and touching things, but oftentimes a UI-driven demo is a little sexier than something that is headless. And then there's only so much time, so we'll just focus on what the query engine can do rather than all aspects of the stack. So let's see what we're going to do. So we'll start. I'm just going to deephaven.io. I'm going to the docs. That's our website. I'm going to the docs. I'm going to the community docs. And then here you'll see how you can install DeepHaven. There's a quick Docker image. You can install it through pip or whatever you'd like. So I'm going to use that Docker image, and now I have DeepHaven running. I'm going to show you the query engine through two interfaces. The first one is Visual Studio Code. I assume some of you are familiar with it. For those that have never seen it before, just bear with me. I'll move to a different interface in just a couple of minutes. So we have a Copilot integration to make your onboarding easy and to help you with your use cases. We also have an extension that will deliver our widgets and other coolness that you'll see in just a moment. So now that I have DeepHaven running, I'm going to start with something that should be familiar to many of you in the room. Is that big enough? So I'm just going to start with a pandas use case. This is the Deep Haven environment. It's truly Python. All I've done is I've grabbed the CSV using pandas, and then I've manipulated that CSV using pandas to find some rolling mins and maxes and some EMAs, and then I've plotted that using Plotly. Okay, this is nothing interesting. This is a intro to data science thing via pandas and Plotly. What I'm going to do next is I'm going to do that exact same thing using Deep Haven. So again, just think, hey, I have table libraries where I'm going to get a CSV. I'm going to calculate some mins and maxes, and then I too am going to use Plotly to draw a plot. Same type of thing. Now we have, a similar thing. All we did is use the Deep Haven interface. So I think maybe you can take it, Faith. Oh, you can do some batchy type of things. In Deep Haven, we can compare it to pandas, but that's not where I want the conversation to go, okay? Instead, what I want to do is I'm going to just go get some real-time data. I'll get it using a Kafka feed in a moment, but first I'll start by just getting real-time data using a WebSocket, okay? So I have a table. This table is the exact same as that pandas table, pandas data frame, or that table I just had a moment ago. The only difference is it is real time, which means it's real time server side, it's real time on the wire protocol, it's real time in the JavaScript API that's supporting this browser app, and it's real time in this viewport that we're seeing. There's lots of things you can do directly from the UI. I'm not going to spend time on this because that's more for the users you serve probably than you. But these widgets are very comprehensive. Okay. And just to get a taste, the last thing I'll do here is I'll do some simple table operations, just like you would with pandas, where, I'll filter the table to just to respective coins, and then I will join them using time series, and I will do some projections and format the table, and then I will create a plot. Right, so just even though I'm sourcing that, so I'm sourcing that data through a WebSocket, and now it is feeding these derived calculations, these projections, these plots. And notice I'm literally just doing using the same type of mental model that you would use in any data frame technology. You can do all this in SQL, obviously, as well, through our calcite parser. You can't do, the graphing obviously would still use our Python handles. I'm just going to go to a different environment so that I'm just going to launch here using Portainer. I don't know if any of you used that before, just a different Docker image on a computer of mine back in Minnesota, because it has a Kafka feed running. So now instead of showing you all of this interaction through sorry, I have to, this one has I put a passcode on it. So server side, I'm doing exactly the same thing, but now I'm in a different environment where I can, instead of going to a WebSocket, I simply configure a Kafka feed, right? So you can see what the configuration is. What's the topic called? What offset do I want to start with, etc. You can inherit this in a number of ways, and you can see that, again, this will be streaming if crypto actually trades in the world. Looks like crypto's not trading as much. And just like before, I can do live filters, I can do live joins, I can do live aggregations, right? And so here I'm binning by minute, and then I'm doing aggregations of those things. And as I suggested before, I can not only do these analytics and have this exploratory experience within that same Python experience as I would with Streamlit or Dash. I can go and launch dashboards that are highly interactive, highly shareable, highly customizable, etc. The other thing that I think is important for you, your constituents, the AI agents that you're trying to facilitate, again, all of the people that stand on top of your shoulders, is being able to move pretty seamlessly between batch and streaming. So we think we're proponents of open formats for batch as well. So so our users tend to use Parquet. They tend to rely on Delta tables and Iceberg tables. And all of these things are well supported within Deephaven, both from a read and a write perspective. So obviously you can exhaust the Kafka, you can exhaust to Parquet and to Iceberg. We support incremental updates to Iceberg from a read and write perspective. And these tables can be large. I think if I hover here, this Iceberg table, not huge, but 174 million rows. Because of the power of viewports, you can move around in it quite well. And if I want to take the Iceberg, right, the batch data and the real-time data, and I want to merge them, for example, it's very easy to do that. You can see that doing operations on streaming data and doing operations on batch data are identical. And if I want to merge them, here's just a binning by minute. You can see that the Iceberg stuff is down here and the Kafka stuff is up here, right? So moving seamlessly between streaming and batch is really interesting. And those wire protocols come into play when we want to connect, I wanted to show you, those wire protocols come into play when we want to connect applications. So I can go to another application, get another table, and inherit it here within this server. So connecting one server to another, and then I can take that table and I can extend the DAG. Such that, you know, if I do, let's just run all that. Come on. So if I can look at the data I brought in remotely since, you know, its aggregation, since it was started a long, long time ago. You can see that, I don't know, $500 billion of Bitcoin has traded since it started. And now I'm subscribing to it and I'm comparing the amount of stuff that is traded since I subscribed a couple of seconds ago to the whole of the last several months, right? And the use cases that you can address here can be sophisticated, such that if I want to, I don't have to do just table operations and time series operations, but I could use scikit-learn and NumPy. I can write my own user-defined functions such that, for example, I want to calculate the betas in real time between Ethereum and Bitcoin. So, you know, all of that is using Python libraries, delivering them server-side, and then updating these live data frames accordingly, such that, you know, if I want to do something like signal processing, such that, you know, I have a raw feed, and then I want to use, you know, AI libraries or ML libraries to do a polynomial fit thereof, all of that will work. So, you know, there's we deliver this technology as I suggest as open source software. If I just Google GitHub Deephaven, you'll find, you know, our repos. We have a lot there. At its core, this is a Java technology. We are maintainers of a library called JPy, which is a Python Java bidirectional bridge that's fundamental to making this feel like a Python first experience. Calcite provides our SQL parsing, so you can use SQL server side and you know, do table and time series operations there. And all the client applications, you know, you've seen an example of that through this JavaScript experience where we have a JS client that's obviously commuting to server side technologies that are doing the work. So I wanted to open it up to Q&A, see if any of this resonates with you, or if there's any questions that this has triggered. On the screen, I have some questions that if anyone wants to talk about afterwards, I happen to be particularly interested in that, and I suppose what your patterns are for bringing real-time data to Iceberg, since that seems to be a pretty hot topic nowadays. Are there, any questions I can provide about Deep Haven's open source technology or the abstraction of live data frames. I think they're bringing a mic to the people from far, far away. And
so is the engine persistent or in memory?
I don't. Where is that? Where did that come from? Oh, there you go. So the memory. So the engine keeps it in memory. It keeps this. So essentially, you're describing the DAG, right? Like you saw that script. Each node in the DAG essentially either has state or has in-memory objects that make it easy to. You can create it as a formula instead of updating the state. So oftentimes community users will choose to write that out, write updates out to something, or snapshot things periodically, or update incrementally to Iceberg tables. In our enterprise product, we're used to supporting Wall Street and e-commerce companies at scale, and so in our enterprise product, we have essentially the shorthand way to describe it is like a Kafka broker for live data frames. So that allows you to essentially write incremental table deltas, that can ingest data from the outside and fan it out, or it allows you to persist live data frames within an enterprise system. But I think that is sort of key. I think it hints on one of the differences between Flink and Deep Haven. Deep Haven's much more for the users that rely on you and sort of the whole company that are trying to run business applications in real time rather than simply persisting or fault tolerant pipelines.
Hi.
Yes.
Could you speak to the execution model, exactly how the stream data and the batch data is being processed?
Yeah, I think I can. So, I mean, we've written a brand new query engine from the ground up. Under the covers, there are different libraries that will be used, unbeknownst to you, as to whether it is a table that can update or a table that is batch. What we've done is we've written methods for all of the operations that are under the covers to be driven by deltas for those incremental tables. So every join for every data type, every time series join, every aggregation, every filter is a completely different methodology that's being written.
Is the execution okay? So those are the operators you're talking about, but the execution of the operators, is it more like a streaming model or a batch model or something else?
Yeah,
how does it stage?
No, so it's much more akin to sort of the way you don't need such a strong deployment model, right? You can deliver an application, and then it essentially is listening for new data and incrementally updating things in real time.
So I had a question regarding the integration with Iceberg, because it seems that you started with sourcing and Iceberg tables, but Iceberg tables can be massive. So depending on how much time that will take, and you also said that as the live data frame gets hydrated or it gets changed, all these can periodically be stored to Iceberg, but it sounds like you will have a lot of delete markers in the place, which will need to be compacted. Is that a problem?
So we tend to think of, there's the work product of the Deep Haven engines, and then we think of Iceberg as mostly a source and a sink, right? It may be an incremental source or a sink, but yes, Iceberg tables can be large. We approach them in batch fashion, in best practices the way others do, where we have strong support for indexes. We use predicate pushdown in the Parquet files that are there. We've strong engineering around the metadata constructs and the catalogs that Iceberg provides. So so navigating large Iceberg tables isn't really such a problem. In regards to the question over here sort of dovetails with what you're contemplating, in that, let's say I have hundreds of applications. Each one of them might have 20 named tables, right? Let's say that's 2,000 named tables that might be getting data from the outside and getting data from each other in real time, updating at frequencies of 10 to 100 milliseconds based on all of those deltas. You're not writing all of that down. You're maintaining memory and state, the stuff that is. And our customers will rely on a couple of things. Either they'll periodically, save states so that they can recover, right? Or they'll use this federation agent, this persistent agent we have in our enterprise product to write things back for recovery and reliability purposes.
So what is a delta?
What is the delta? I mean, so a delta is really just this. It's really just an add, a remove, a modification, or a reordering. So when you look at the exhaust of a table to a client, so for example, if you listen to a table, you'll get a stream of deltas that specifically identifies all of these attributes. And within the engine, the engine operations are organized to be able to do dynamic relational algebra, but by taking the previous state, taking those deltas, and then updating the state of the data frame. It's really what happens is I don't like this word because it can be a little confusing, but you'll set up a micro batching frequency within any process. Let's say it's 10 milliseconds or 100 milliseconds, just so you can there's efficiencies that come from not responding to every single new tick that comes in from Kafka. So let's say it's 100 milliseconds, and what happens is you'll receive data for 100 milliseconds, and then you have a guarantee that within the process, the process won't update any of the tables, won't update any of the nodes until it can guarantee that it's updated all of the nodes. So within that process, at the end of the 100 milliseconds, you will have state of all the nodes that are consistent with one another. Obviously, if you have a script or application that has too much work such that it didn't get done in 100 milliseconds, then that'll be violated, to take 200 milliseconds, and then the next thing will launch with all the data that arrived. But essentially, all the nodes within a single process will always have states that are consistent with the source data within that time window.
So we have one question from our remote participants. Mahesh asks, how easy is it to integrate Deephaven with existing data lake houses or warehouses like Snowflake or Redshift?
Sure. So, I think there's two aspects of this. One is, Snowflake has a database and a data lake element to what they're doing, right? The data lake element, they're huge Parquet users and huge Iceberg. They're all in on Iceberg as well. So they're writing and reading the Parquet and Iceberg. We're writing and reading the Iceberg as well. There's, maybe 10 engines or 15 engines that are pretty good that can do that type of stuff. So that integration is key. In regards to other integrations with databases like Redshift or like Snowflake in the database side, we can both drive and query databases via ODBC, ADBC, and Flight SQL. So you can query Snowflake no problem just by sending a SQL query via ODBC, or you can take a snapshot of Deephaven or use CDC to get changes from Deephaven into your classic database infrastructure.
No. Right. Thank you, Pete.
Great. Thank you, Barry. Thanks, everybody.
Our next speaker is Onur. Onur is a senior staff engineer at LinkedIn with an interest in distributed systems. He is the tech lead of Northguard, a log storage system with a focus on scalability and operability. Prior to Northguard, Onur was a committer to Apache Kafka, where he focused on Kafka's scalability. He redesigned the cluster's controller, made the controller use Zookeeper's async APIs, and worked on the group coordinator and consumer group management protocol. With that, I think Onur is getting prepared for the next session. The title of the talk is Northguard, Scalable Log Storage at LinkedIn.
Hey everyone. Sorry about that. I need to grab some water. Okay. Yeah. So let's talk about Northguard. All right. So first, let's take a step back and talk about log storage in general at LinkedIn. So log storage is used all over the place at LinkedIn. It's used for like observability, for logging, metrics, tracing, as well as like application-to-application messaging, as well as like near real-time applications such as like stream processing use cases. And we even use it for getting data in and out of data lakes, as well as for more core infrastructure like database replication and AI feature training. And the scale that we've been operating at has been pretty mind-blowing. So we have over 32 trillion records per day. And that amounts to something like 17 petabytes per day. And this is done over hundreds of thousands of topics. And to support that, we're running about 10,000 brokers. And these brokers are divided up into something like 150 clusters. But running at this scale has led to several major challenges. First of which being scalability. So we're effectively already at a point where we've been hitting scalability limits of Kafka. An example of this is our Samza use case, where we've had to stand up clusters multiple times now because they run into metadata limits in the Kafka cluster. And so when we stand up multiple of these clusters, eventually you end up with these 150 clusters. And now that you have these over 100 clusters, now you have to worry about how to operate them. And each of these clusters might have separate planning as well as deployments to worry about as well. And one other aspect of operability is that Kafka has the notion of partitions, and partitions are its unit of replication. And when you have partitions where the entire partition lands on a broker, then you risk the chance of multiple partitions that are relatively heavyweight landing on the same broker, and that can lead to load skew in the system. So then you need to worry about how do I actually manage this load skew. And for that, LinkedIn has developed an ecosystem to support that. And for example, we've developed cruise control to even out the load distribution by strategically placing partitions on a good combination of brokers in the system. Other challenges that exist are availability. So when you have these partitions that are residing on brokers, you now have to worry about if a failure of a replica happens on this partition, now you're effectively on the clock to re-replicate that partition up to its original replication factor. And until then, your partition is effectively in like a somewhat degraded producing consume availability. Right, and another challenge that we see is that we have many use cases that want more durability. And today, as we've configured Kafka at LinkedIn, you can lose up to 10 seconds of data when there's like a power outage. Okay, so to address these challenges, we've developed Northguard, a log storage system with a focus on scalability and operability. Okay, so although scalability and operability are some of the key goals, there are others as well: availability, consistency, functionality, and testability. I'm not going to go over all these, but we'll focus on a few key points throughout the slides. Okay, so before we get into the key concepts, let's just talk about the building blocks first. So at the bottom, we have records, and records are the most granular unit of data to be read or written. And it's comprised of headers, a key, and a value, and these are just bytes. And these records could get sequenced into a segment. And this segment is the unit of replication in Northguard. And that means that we define replica sets at the segment level. And segment can either be active, that means that producers can continue to append to the segment, or it can be sealed, which means that it's immutable and you can no longer append to it. And we could build up a sequence of these segments. And this is essentially our range abstraction in Northguard. And this range, you could kind of think of it as our version of the log abstraction. In Kafka, the rough analog would be the partition, except that we also have an additional concept of a key space attached to a range. So similar to a segment, a range can be active, which means that the range is appendable. And that means that a range can have an active segment in it. Or the range is sealed, which means that a range cannot have an active segment in it. And so the range is no longer appendable. And these ranges can be split or merged, and we use these seal ranges as part of that process. So when we want to split a range, we seal it and then make two new ones. Right, so at the very top abstraction, we have topics, and a topic is just like a collection of these ranges that cover the full key space. And here you can see, for example, like R2 gets split into R4 and R5, and then maybe we decide to merge R4 and R5 back into R6 later on. Okay, so let's go over some key concepts. The first of which I'm going to refer to as log striping, or you could think of it kind of like chunking. But the basic idea is we have this range, and this range has some number of segments, S1, S2, S3, and these segments each have, let's say, 3 replicas, right? So these gray boxes would be some brokers that are existing in the system, and maybe S2 has a replica here, here, and here, right? But you'll notice that there's a broker where there is no segment residing on it. With log striping, what we're going to see is that soon enough, S3 will get sealed and we'll create a new segment, S4. And when we do that, that's an opportunity to come up with a new replica set, which could potentially decide to use this new broker. So, for example, S4 happens to land on the new broker as well as these other ones. So this is really nice because it naturally lends itself to self-balancing clusters, as well as when we add new brokers to a cluster, that new broker just immediately starts getting used without having to move like pre-existing data onto that new broker. So that's very nice from an operations standpoint. Okay, but how did we actually decide the replica set when we made that S4 earlier? For that, we have these notions of attributes and policies. So policies, or I guess I'll with attributes. Attributes are just like key value pairs that administrators define and they kind of like bind to a broker. And these are just opaque bytes to Northguard. It has no interpretation of what these keys and values are, but just some examples of how you might run this in production. Maybe like you might want to attach some like data center information or a rack location, or maybe a role or a pool, for a random example. And these policies, you can use policies to define how the replica sets are chosen for the segment. And these policies are defined by administrators. So you might say, for example, I want my topics segments to have 2-day retention with 3 replicas, all of which are in the same pool. Any pool is fine, doesn't matter. And with the role that's like a storage broker, and it's in the West data center, and it has a distinct rack location. We could express that with policies today. Okay, and with ranges, we get some nice ordering guarantees. The first of which is that a range is a total ordering of records. And that's because a range is a total ordering of segments, and a segment is a total ordering of records within the segment. So you could just make that transitive plain. And then when we split a range, we could also make some ordering guarantees as well. So let's say that we have this R1 and R2 and R3 here. If we split R1 into R2 and R3, we first seal R1 to create R2 and R3. And therefore, we could claim that all the records in R1 happen before the records in R2, and all the records in R1 happen before the records in R3. And when we merge, we could also make total ordering claims. So when we merge R2 and R3 into R4, all the records in R2 and R3 happens before the records in R4. And again, when we do this merge, we're doing the seal on R2 and R3 first before creating R4. Okay, so that kind of covers some of the key concepts of the data side, but let's go over what the metadata looks like. So at the bottom, we have the notion of a vnode. We're using the term incorrectly here, but the vnode concept is that we have a fault-tolerant replicated state machine, and that state machine internally is backed by Raft, and this state machine stores like some shard of the cluster's overall metadata, whether that's topics or ranges or segments. And one layer above that abstraction is we have coordinators, and this coordinator is the leader of a given vnode, and that's just one-to-one with whatever the underlying Raft group of that vnode was. That is the coordinator for the vnode. And this coordinator manages all the metadata owned by a vnode. And this means that it's like responsible for like the business logic of any metadata that's owned by that vnode. Some examples of this might be like if there's any like protocols that are associated with metadata, that coordinator would be responsible for carrying it out. 1 second, sorry. Okay. And what we can do is scale this out. And we do that by having many vnodes in the system. So that abstraction is the DSRSN. So the DSRSN is a dynamically sharded replicated state machine. And you can think of this as a collection of vnodes covering the hash ring. And what we're doing is anytime that there's like a piece of metadata, we map it onto the hash ring, and whichever vnode owns that region of the hash ring is the vnode that's responsible for that metadata. And one thing I want to call out is that, so let's say that this vnode 1 is here, it might own this region, vnode 2 is region here, for example. But one thing I want to call out is that the position of this vnode doesn't change when the underlying replicas of the Raft group come and go. So that's pretty important. So yeah, basically vnodes stay in place in the position in the hash ring. And for how routing of the metadata works, when it comes to topics, we just take the hash of the topic name, maybe that lands here for add click event. And in this case, it looks like V2 manages that add click event topic metadata. Whereas maybe page view event, we take hash of it, it lands here. And maybe vnode 3 is responsible for the page view event topic metadata. We do the same thing for range metadata. So we take the hash of the range, and whichever vnode is responsible for that region, then they own that range. Okay, and we can also split vnodes. So you can imagine that we have a vnode here, and we decide that it's time to split. What we're going to do is break the state in half and give, like, basically spawn another Raft group. It could completely overlap with the members of the previous Raft group potentially, and then they just break off with that half of the state. Okay. So with data model out of the way and metadata model out of the way, let's talk about what kind of cluster membership and state there are. And for that, let's talk about SWIM. We're using SWIM protocol as the group membership protocol. You can just think of SWIM as like this very scalable gossip-based failure detector. But there's kind of two parts. There's like a failure detection part as well as like a dissemination part. I'll go into detail about that later. Yeah, so for the failure detector, what we're doing is like every like round of time, each member like randomly probes a few other members. And that gives us good time to first detection. And it's kind of like independent of the cluster size. And there's also the dissemination path. And what that means is like, okay, let's say one member discovered that another member of the group failed. How do we actually tell everyone about it? And for that, there's like this infection style broadcast that occurs. And that gives us like really fast broadcast of the news of a failure to the rest of the cluster. And we also use this dissemination for spreading some minimal global like cluster metadata as well. Okay, so let's talk about some protocols. So we have both unary and streaming protocols. With unary protocols, that's more associated with like the metadata requests that we have. And we also have streaming protocols, and that's more for the read-write path, right? So that would include our produce protocol, consume, and replication. Okay, So with streaming protocols, there's essentially a streaming handshake that takes place where we sessionize some state up front so that we don't have to keep sending it around. And that means that like later requests under that stream don't need to replay that same information. And we make use of pipelining. So on the produce protocol, we pipeline appends, which means that we could send a bunch of appends over the wire without waiting on an ACK up until a point. And on the consume protocol, the broker can send a bunch of pushed messages over to the consumer over the wire without waiting on redac up until a point. And replication, similarly, the leader can push replica appends to followers over the wire without waiting on an ACK. And how much we could send over the wire at any given point in time is based on how much windowing is afforded over that stream. Okay. As an example, we have a producer here and a broker here, and we might have an append. I'm assuming that the handshake already took place and we decided on the stream ID. Let's just say it was 3 here. And append includes the stream as well as some amount of records, as well as a sequence number. And maybe it sends more appends later on, where it updates the sequence number as well as provides additional records and so on and so on. And in the opposite direction, the broker is sending ACKs to the producer. And this ACK has the same stream ID that came from the produce, as well as an acknowledgement number, which correlates to the sequence number provided from the append, as well as a window that the broker defines that it can update over time that expresses how many messages can be pipelined at once. Okay, consume is pretty similar, except it kind of goes in the opposite direction in some sense. So the broker is sending pushes to the consumer, and this push has some amount of records. Again, there's a stream ID. This time, instead of sequence numbers, we've already agreed on an offset, so it contains the offset of the records. And consumers send what we're calling reads. You kind of think that's a read ACK, where the consumer is expressing what it has acknowledged reading so far, as well as potentially an updated window. And replication, again, works very similarly. The leader would send replica appends to followers with messages and an offset, as well as potentially an update to what's been considered committed so far, so that followers can learn of progress of commit. And followers send replica ACKs back to the leader, where it would inform what it has durably stored to disk. And it sends this offset back of what's been durably stored, as well as potentially updating the window. Okay. When it comes to testability, we are testing with thousands of tests. They run pretty quickly. We also have micro benchmarks and a pretty elaborate certification pipeline. The certification pipeline involves a certification cluster that's taking synthetic traffic, and we're doing all the common admin operations we would do on a cluster, like deploy the build, roll back the build, kill a broker, bring it back up, pull the power plug off. Okay, that's not a common admin operation, but we prepare for that anyways. So we pull the power off of a broker, as well as other tests as well. And we're checking that the availability, producing consume availability still looks good despite us messing about on the cluster. And there's also periodic stress tests that we run. And we also developed a deterministic simulation framework that I'll go into now. So yeah, what we have is this framework where we can run a Northguard cluster as well as its clients fully deterministically on a single thread. And we're doing this through dependency injection of replacing all the non-deterministic bits of a broker with deterministic versions of them. So you could think of like time, network, disk, DNS, random number generators, etc. We just swap in a deterministic version of them. And we also can inject faults at the same time, like deployments, rolling restarts, network partitions, different types of corruption, errors, and even like config deployments we can simulate. And so with that, we define these scenarios where we try to throw in a bunch of these types of faults, and we set up some sort of workload. And every night we run all these scenarios thousands and thousands of times under different seeds. And collectively, we're simulating like years of execution every night. And what that means is like for every like real time, like second that occurred, we might be simulating like, I'm going to make an example of like 30 seconds worth of time. And that might work because like if there's any amount of downtime in a broker where it's like idle or doing nothing, it just simply skips ahead to the next task instead of waiting for that amount of time to occur. With this framework, we're able to catch a lot of bugs early. So that's pretty neat. Okay. Let's talk about evaluation. Right, so for scalability, when it comes to data, Kafka has logs or the partition bound by the machine disk capacity. Now this isn't fully true if you're using tiered storage, but in non-tiered storage mode, this is the case. And in Northguard, the difference is that the logs are bound by the cluster disk capacity. When it comes to the metadata control plane, Kafka has essentially one replicated state machine, and we see this getting stressed at millions of partition replicas. In Northguard, our hash ring has like over 100 of these vnodes, and that we see it doing just fine at the scale with millions of segment replicas and ranges. And when it comes to metadata distribution, we see that Kafka does global topic metadata state, whereas in Northguard, we have very minimal global state. And what I mean by that is instead of spreading out like news about every single topic or partition or what have you globally to every broker in the cluster, the only state that we have in Northguard that everyone knows about is what are the vnodes, which brokers are alive or dead, like what are the like hosts and ports of these brokers, like that kind of very minimal state. Right, and for cluster size, in other words, like when it comes to group membership, we see centralized group membership part beating to the controller in Kafka, but in Northguard we have this decentralized, scalable, gossip-based group membership. When it comes to operability, as I said before, we were running over 100 Kafka clusters. We're thinking we could get away with like 3 to 12 Northguard clusters, something in that ballpark. And for data distribution, whereas we have relied on cruise control and external service to keep our Kafka clusters balanced, in Northguard, it's balanced by design, by the nature of its striping. And for metadata distribution, there really isn't an analogous concept, I think, in Kafka, that because there is this single replicated state machine. Whereas in Northguard, we have these many vnodes, and the replicas of these vnodes are chosen in a way that's balanced as well. Right, and for adding brokers, when we add a broker to the Kafka cluster, it won't have any new partitions assigned to it unless we create a new partition after the fact. So realistically, to make that broker be used, we have to move existing data onto that new broker to actually have it start doing things. Whereas in Northguard, you just start up the broker process and data is flowing through it like in seconds. And when it comes to replenishing the replication factor, again, we rely on cruise control to decide what the right broker should be to replenish the replication in a way that keeps the cluster balanced. In Northguard, this is out of the box. Yeah, so like we just have the coordinators decide who should be elected, and they're on their way. And they're using these policies from earlier to make sure that it's making a safe choice. Okay. For availability, we see that in Kafka, because of the partition being the unit of replication, the produce availability degrades as replicas fail. And again, you're on the clock for re-replicating in time before additional replicas fail and potentially risk taking the partition offline. In contrast, in Northguard, because we have striping, we get higher availability. If you're producing to a segment and there's a broker that fails on that segment, we just seal it, make a new one, move the producers over to that new segment. And yeah, so produce availability just stays good. We just move producers over. Consistency, right? So because, like, again, of the partition needing to re-replicate in time, we often choose at LinkedIn to favor availability over consistency. And we instead like to avoid that kind of situation if possible. So again, with segments as the unit of replication and log striping, when a replica of an active segment fails, again, we just make a new segment and move producers over to it. So there isn't really that race to replenish the replication factor anymore. So we don't really have to make that trade-off that eagerly anymore about consistency and availability. Okay. And for durability, Kafka has lazy syncs. So when I get my ACK as a producer client, I know that it's been replicated to some degree, depending on how it's configured, but I don't know that it's necessarily been written to disk yet. And so it uses lazy syncs, which means that each replica is going to periodically flush to disk, either, and how we've been configuring it is every 10 seconds or every 20,000 records. But that happens asynchronously from us giving the producer their acknowledgement. This is in contrast to Northguard, where we're f-syncing on all replicas before produce ACK. And we're doing this every 10 milliseconds or every 20,000 records or every 10 megabytes. So you know when you get your ACK that like it's actually on the disk. And we're doing this while meeting LinkedIn's SLOs for Kafka, but with better durability. Yep. And we've had a great team that helped us, that got us there. And as for what's next, we want to continue to ramp up more traffic. We want to continue to make more performance improvements, as well as provide low latency offering, geo-redundant storage, and try to get it open source as well. Yeah, that's good.
Thank you. Oh, a lot of questions.
First, congratulations. I think a big shout out to the team to actually come to this milestone. So thank you. Awesome logo, by the way. But now to the question. So most of the data is going to be on cloud storage. Where do you see the future instead of using local storage and then going to a completely stateless log storage?
Yeah. So I think there is there are kind of like two key concepts here. One is like tiering, or to some extent you kind of think of it like tiering. The other approach, the other orthogonal concept, I think, is striping. So I still think there's benefits even with this kind of remote storage world where you actually still want log striping. And there are applications as well that they want to have low latency consumption, for example. And sometimes you can't really get that with remote storage options. And there are scenarios I could think of, even actually just a few days ago, where like we had a service where they might have fallen quite far behind, and they have some pretty strict requirements about being able to catch up quickly despite having fallen quite far behind in their log. So I think there's a risk of if we prematurely say like, oh, everything is going to go to like some sort of tiered storage solution, where these kind of applications, they might not actually be able to catch up in time in some certain situations. So I think we need a good solution for local storage to give you those fast consume and catch up scenarios. And maybe for applications that care less about catching up quickly, maybe there it makes sense to evaluate remote storage options that are like maybe cheaper or whatever.
Yeah, I was looking at the data model. It looks the same as Apache Bookkeeper, or is there any difference?
Apache Bookkeeper. Okay, yeah. So a few differences. So we did evaluate that early on. One is that with Northguard, there really aren't any like system dependencies. So like meaning that like you don't need another system to be propped up in order to run Northguard. Bookkeeper has a dependency on Zookeeper, last I checked at least. Another difference that I could think of is Bookkeeper only has the log abstraction, which is a great abstraction to have. There are other applications though that want to have that more out-of-the-box experience of like a topic that you could have multiple ranges and be able to produce a mix of them. Yeah, so Pulsar, again, so when we consider Pulsar depends on Bookkeeper, which depends on Zookeeper. So now you have three services to run your system. Yeah.
I have two questions. The first one was around splitting ranges. I imagine it's for pretty much when you need to rebalance segments. But after merging two segments, the question was, is that an operation that you would perform in order to free up space? Or why would you actually get rid of R2 and 3 in this case in order to merge them into R4?
Got it. Okay. So I should clarify that when we do a split or merge, we're not like actually combining data at all. So like the segments that were in this R2 and R3, they're going to stay there. we're not going to like fuse together two segments or something like that. Yeah, so they stay immutable. You know,
So it's just like a logical a grouping of these things, but I assume that you needed to split a range in order to rebalance segments or something like that. Then why would you do the logical splitting of segments? What would be the use case in this case for R1 to go into this split into these two segments or these two new ranges? I mean.
Right. So why do we split ranges? Is the question.
Mm-hmm.
Yeah. So anytime you want to like have more like logs in your topic, you could split ranges to create another one, for example. So like, let's say that you have a topic and let's say you're hitting some sort of scale limits of the given set of logs that you have. Maybe you want to have more throughput. Then you would add another log through a split range, for example.
I'm still confused on that part because
sure.
if these ranges are local to a broker, right? Or a range constitutes segments across brokers.
So a range is just like this piece of metadata. It doesn't actually like get persisted anywhere.
Okay.
The range has a segment, and the segment has replicas. And those replicas are like the brokers storing those segment replicas.
Okay, because I understood that the parity between ranges and partitions on Kafka were kind of the same, but if these are more of like a logical structure and segments are the ones that actually live across brokers, because your producer is the one actually writing the segments, right, separately. Why not kind of like rationalize that the segment is actually the new kind of like partition equivalent to Kafka?
You could think of it as a small chunk of the Kafka partition, kind of.
Yeah. Okay.
So instead of assigning the replica set at the partition level in Kafka, we're going to break it up into smaller pieces, and those smaller pieces have a replica set instead. That's the core difference.
Okay, sorry. I have more questions to ask afterwards.
Sure. Yeah.
Two more questions.
Can I ask next one?
Sure.
Congratulations to the team on this achievement. And over this multi-year journey, what would you say was like much harder than you initially thought?
Oh, okay. I had a list of like 40-something questions. I was not prepared for that one. What was harder than I thought? Let's see. So, I guess there's a lot of things that are coming to mind, but I'll just say one of them. Initially, the way that we have developed the code, as you know, is we kind of went from like a use case first, like let's hit some milestone of the use case and try to meet that level of requirements. And then we like rinse and repeat and like get bigger and bigger use cases and then try to meet that use case. That's how we've been operating. I think one particularly difficult phase was like basically the first time we actually tried to like improve the performance of the system. So that was one thing that comes to mind, but we went through it and we're in a good spot now. Yeah. As for other difficult parts, I think that's like the main one that comes to mind. Yeah.
There's so many interesting nuggets here, but I'll restrict my question to one, the simulation testing.
Yeah.
Is it something that tied very strongly to this particular project, or is it something that you could independently release it and could be used by other systems and languages and runtimes?
Yeah. So it's kind of coupled, honestly. I think you could probably reuse some of the code, but we okay. But when it comes to deterministic simulation, like one of the key things you have to tackle is like how do you get a hold of the scheduling, right? Because if you're just naively like spinning up threads, then like how do you actually control those threads? So if you were to adopt our framework, that kind of means you're also buying into our solution to that problem, which I didn't even get to at all here, but we basically have like many event loops inside the broker, and there's like message passing that's happening inside the broker. And that's kind of how we solve that problem, is that like we abstract away the actual concurrency and scheduling through those through that event bus system that we have. So it's maybe possible, but maybe not the most easy to do. Yeah.
All right. Thank you very much. Thank you, Anur. Great presentation and great tool.
All right, thanks, Onur. Our next speakers are Wesley and Ku. Wesley is a senior staff engineer at LinkedIn. He joined LinkedIn Kafka team, now Streams.io team, in 2018. He worked on Kafka broker scaling and LinkedIn Kafka clients ecosystem previously. He currently focuses on the virtualized PubSub system known as Northguard-Xinfra. Ku is a staff engineer at LinkedIn. He joined LinkedIn Kafka team in 2018. He worked on Kafka clients, Streamline at LinkedIn and Kafka ecosystem previously. He currently focuses on the virtualized metadata control layer in Northguard-Xinfra. With that, I will leave it to Wesley.
Thanks, everyone. Today, I and Ke will talk about Northguard-Xinfra, which is a virtualized PubSub layer. So before we talk about the problem we are showing, let's look at the current PubSub scale at LinkedIn. So some of the owners talks cover about that we are running actually tens of trillions messages per day, and there's hundreds of thousands topics and thousands of applications. And we also have tens of billions of PubSub clients. So PubSub clients, including Kafka clients, Northguard clients. So with that scale, we are actually having some problem. One is the PubSub migration. So there's two aspects of the migration. One is migrating topic from one Kafka cluster to another Kafka cluster. So essentially migrating topic within the same ecosystem, but to a different cluster. So the second aspect is what happens if we need to migrate topic between different systems. Now we have topic that currently existing in Kafka cluster, and we want to migrate those topics to a Northguard cluster. So it's be even difficult because imagine there's running application, running producer, consumer. So we do not want to cause any downtime of those clients. The second problem is the single cluster limitation. So in the previous talk, we also mentioned that often we need to adding cluster in order to accommodate the traffic growth. However, adding the cluster is not transparent to our application. So it often requires application to change their configuration, point to a different Kafka cluster, redeploy their application. So the process is not smooth. And a third problem is when it comes to dealing with more than one Kafka cluster, we have thousands of clusters. In some use cases, there's a topic and clients that's running on different cluster. A problem with this is the topic and client configuration. They usually diverge across cluster. It's really difficult to detect some of the configuration or some of the client property that's so there's two main part of this talk. First we'll go over this virtualized PubSub layer that's on top of Kafka and Northguard. Then second, we are talking about how we're doing migration from Kafka to Northguard in LinkedIn. So this is the overall stack of we are currently running. So at the right-hand side, you can see we are running Kafka brokers and the Northguard brokers. And in the top, we have two services. You can think of this as our Xinfra metadata layer. And in the center, we have clients. So clients is the place that user application interact with. The clients now like talk to our metadata layer and also talk to Kafka and the Northguard broker for sending data and consuming data back. So let's now look at the basic building block of this virtualized layer. So the Xinfra is like virtualized PubSub layer. Like it's supposed to be used for different PubSub system. So what it makes so like difference is it has concept called virtual topic, and topic as epochs, and Xinfra topic can be created first at Kafka cluster, and at a later time it can be like moved to a different cluster. So Xinfra is virtual topic concept, and the virtual topic life cycle is not necessarily coupled with the physical cluster. So there's dynamic like of the topic. And what does this like virtualized concept give us? One is it enable the switch between workloads. So previously, before Xinfra, we like users always have topic in one single Kafka cluster, but with the Xinfra, it enable the like movement of the topic. So another big benefit is yes, like enable native federation. With the Kafka topic, like usually in a single cluster, like adding topic is not transparent, or adding topic to more than one cluster is even like sometimes require like application spin up more than one client, point to different cluster. However, with the Xinfra, so topic can be like grouped under the same virtualized namespace. You can think about the namespace as a virtual cluster concept. So a virtual namespace or virtual cluster can be underlined backed by like more than one physical Kafka or Northguard cluster. So the Xinfra also providing us ability to have a centralized place that we can manage all clients and the configuration. This also enable us to like safely rolling out some of the like features without restarting our clients. So let's look at the like the data model of this Xinfra. So we compare the Xinfra data model with the Kafka. So it pretty much like Kafka. However, the key difference is the Kafka is a single physical topic. However, with Xinfra is multi-epoch topic that's underlying can be like backed by one or more physical topic. So Kafka has partition, and the Xinfra has shards. Each shard is like the app. So Xinfra topic contains like multiple epochs. Like each epoch contains list of the shard. The shard is pretty much the concept of the Kafka partition. So Kafka has offsets, and in Xinfra we have also have offset, but they're slightly different. So the offset is like opaque or transparent. So reason we have the transparent offset because we want to support a different system, and we also want to involve the offset without breaking application. So like for example, in Kafka, people assuming this is not offset. There's no much room we can like feed into a different metadata or additional information into the offset. But with the opaque offsets, we can like freely supporting different system or adding some features. And Kafka has records with its key value headers like Xinfra also has records. Its key value headers. From user's perspective, it looks very similar. And we also have admin client producers as consumer, also pretty much like Kafka. So the user interact with the Xinfra stack through the Xinfra clients. So the client is providing a unified PubSub API. Currently, is work for both for Kafka and the Northguard. And once users like application adapt the Xinfra clients, it get the like couple of functionality. One is enable the transparent migration from Kafka and Northguard. So this doesn't require any like user change, like vertical application. So we'll talk about the migration in the later slides. And there's a set of features we also get with the clients once we do per record compression, which essentially have a better compression efficiency for low volume traffic. Also providing a comparable compression efficiency for high volume traffic comparing to the Kafka compression. And we also support large message. The large message meaning that if some producer sending some big records that is higher than broker's limit, so the client will do like split and assemble it on the consumer side. And as I mentioned earlier, it's for native federation. A single client can talk to like more than one cluster. From customer point of view, is a like single virtual cluster. And it's supporting client configuration without restarting the client. There will be like some configuration that get pushed down from our Xinfra metadata layer that's enable us to rolling out features, dynamic disable, like certain features or like configuration. And the client API. So it's pretty much like Kafka style API. We have admin API, which supporting CRUD operation, create topic, the topic, update topic. And we have producer API, which is we have providing two style of produce. One is produce to a shard, which is something like Kafka produce to a partition. And we also have producer topic API, which is the shard of partition is automatically selected by the client. And consumer API will also have two flavors. One is like menu assignment, and the other is the subscription based. This is a consumer group based. And next, I will hand over to Kerr to talk about the Xinfra metadata layer.
Thanks, Wesley, for the overview. Next, I'm going to talk about the Northguard-Xinfra metadata layer. So the Northguard-Xinfra metadata layer is a virtual layer that provides a unified view of underlying pub subsystems. It consists of two major components. One is called XMD, the Xinfra metadata service, which is a topic metadata store. Another is called Conductor, which is a client-facing service that provides the feature of consumer group management, checkpoint storage, and client management. A very high-level workflow of how the Xinfra clients interact with the metadata layer is as follows. First, the users can create a topic with Xinfra admin client. The request goes into Xinfra metadata service and goes to MySQL as source of truth. And once the topic is created, the users can start producing to and consuming from the topic. with Xinfra clients. So when the client started, they will talk to conductor to fetch the topic metadata. The conductor will fetch metadata from XMD and store it in an internal cache. And for consumers, the position store component inside conductor will write the checkpoint positions to MySQL as source of truth. We'll dive deep into each of the components in the next few slides. So next, let's take a look at XMD. And first, let's take a look into the data model. So Wesley briefly mentioned the abstractions we provide to users. Here are a few key concepts. The first one is called topic. So, and the users are exposed to a virtual topic concept. Unlike Kafka topic, which is a simple topic name, in Xinfra, the topic is uniquely defined with a namespace, a topic, and a zone. And underneath, there can be multiple physical topics, which represents an actual Kafka or Northguard topic. And one topic, one virtual topic, usually consists of multiple topic epochs, with each topic epoch captures one Kafka or Northguard. In this example here, the users are only dealing with the virtual topic, namespace / page event / zone here. And underneath, topic is first created in Kafka cluster and later migrated to a Northguard. We also expose topic properties to users, which includes both the virtual topic properties that are generic, as well as PubSub specific topics. And last, we also expose namespaces, zones, and clusters for failure separations. You can always create your own namespaces, zones, clusters as needed. So what is XMD? It's a virtual metadata layer that provides a unified view of different PubSub systems. By managing the mapping between virtual and physical topic shards. With that, it enables better topic scaling, topic management, and transparent topic migration to users. And as to the APIs, it supports the regular topic CRUD operations, as well as the topic migrations from Kafka to Northguard and vice versa. And as mentioned, it provides the namespace on cluster registration. And it also provides the cluster federation, which can map one namespace to multiple clusters, multiple PubSub clusters, hiding the complexities to end users. So that's for XMD. And next, let's take a look at Conductor. Conductor is a client management layer that provides the following PubSub facilities: client management, consumer group management, and checkpoint storage. So the first component is client management. For each Xinfra producer consumer, it maintains a connection between itself and Conductor. This allows us to track the client's relations, their configurations, as well as the topics of interest. And it also maintains a metadata cache for topics, so that it doesn't need to query XMD every single time. And the next component is consumer group management, which is usually called CGM. Since Xinfra is PubSub agnostic, Conductor consumer group management manages virtual shards, which naturally supports consuming from different PubSub systems and clusters. In this case, Conductor serves as a group coordinator with a consistent core backed by Zookeeper. A few key features of consumer group management is, first is incremental group balancing. Instead of stop the world one, only the certain consumers and shards involved in the rebalance will need to be involved. And all the other consumers will remain consuming as expected. It also ensures fairness in shard allocation while minimizing the movements across consumers and shards, thus minimizing the service disruptions. And last, it is also fault tolerance to various error scenarios like consumer crashes, conductor crashes, etc. One last component for Conductor is called checkpoint storage or position storage, which is a common requirement for consumer applications to keep track of their consumed positions so that they can resume when it restarts. And then Conductor is done with the position store component, which uses Couchbase as a caching layer plus MySQL with coalescing buffer as a source of truth to achieve fast checkpoint store and fetch. That's all for the Northguard-Xinfra layer. With that, I'll hand it back to Wesley for the migration status.
So let's look at the current migration status. So since we introduced Northguard, so the company-wise, we are like migrating our traffic from Kafka to Northguard. So currently, we already have trillions of records per day being migrated to Northguard, which is equivalent to like traffic 10 years Kafka traffic after we introduced the Kafka. And like we kind of established several principles how we're doing the migration. So one is we want to do a seamless migration because we don't want to impacting our application. And second, we want to gradually roll out this migration on a topic by topic basis. So if anything like it's not working as expected, it's only impacting certain topic. And always want to start with the low risk topic and to high risk topic. And during this migration process, and we want to proactively monitor the clients, the servers metrics to making sure that the migration works. So in order to achieve this principle, so we built some key features. One is the topic selection. So we only want to select topic that meet certain criteria, such as when order, like producer, consumer interact with the topic beyond certain versions, that we know those clients are good and only migrating those topics. There are other rules we apply on how we select the topic to migrate is such as like I mentioned, is always start with low risk topic, that topic or data that do not cause any revenue impact. And we want to do live migration. This will be transparent to our customer. We do it on a topic basis, and we have like dual right during migration, which means that producer will produce to both Kafka or Northguard topic, assuming we are migrating from Kafka to Northguard, and those dual right data providing us ability to fall back if in case anything go wrong, and there will be no downtime for producer and consumer during this process, and we can do live fallback. If anything go wrong during this process, we can fall back to original topic without the loss of data. And we also built some external verification or external validation service. During this migration process, this external service will read the data from both location, verify the data consistency, verify everything looks fine, like metrics, and we only like migrate topic if everything looks good. And we also build centralized monitoring, which means that all the sample clients emitting client metrics, emitting client log to a centralized location, which the team can take a look at and to find out if any like suspicious metrics, any errors, any logs, like that we can act quickly if identify the error during this process. So let's take a deep look into how the migration works. So in this diagram, the rectangle represents the virtual epoch, and at the beginning, imagine a topic as single epoch, which is in a Kafka cluster, and the first step of migrating topic is we migrating the producer. The way producer being migrated is we're creating a new topic epoch in a Northguard cluster, and the Kafka cluster or the data in the Kafka topic is still the source of truth. Producer dual write to Kafka and Northguard cluster, whereas the consumer still consuming from Kafka cluster at this stage. And at later point, we migrate the consumer, there will be a like boundary or records by our metadata system. Then consumer when consume till the boundary, like till the end of Kafka topic, then consumer will be continue through a new epoch, which is the Northguard cluster. If anything go wrong during this two process, then we can fall back to a Kafka cluster. The way the fallback works is creating a new epoch, which reuse the same physical Kafka topic. So, and we set a special state on the Northguard epoch, saying that both consumer and producer will ignore the whatever data in the Northguard cluster. The fallback, after the fallback, the data will reside in a single cluster again. If everything went smoothly, then we can turn off the dual writes, which will complete the migration, and the Northguard cluster become like read-write cluster versus the Kafka still used for the read, because there might be data in the Kafka cluster. We don't like move the data around, so we still need to keep the data in the Kafka cluster readable. And after the data retention, then we can become a single like epoch, a single data will be in the Northguard cluster for both consumer and producer. So couple of the migration insights. One is the opaque switch between Kafka and Northguard. This will be transparent to our customer, and consumer like the Xinfra will understand different representation of the consumer position. Then the consumer will be smoothly transit across the Kafka cluster to Northguard cluster. And the other things was called out because of the dual produce. There will be data overlap when we switch the consumer, which means that the consumer may experience some of the rewind. So how much the rewind is the time is the amount of data is configurable. And we are also working on some digitation solution in the consumer for some like debug sensitive application. And typically the dual writes will last for a few hours. Why a few hours? Because we want to like verify things working, and also providing us a time window that's the client can be fallback if there's something wrong in the new cluster. So this solution not only work from the Kafka to Northguard, but also for Kafka to Kafka. And I briefly mentioned earlier that the Xinfra offset is opaque. So it's reason for opaque. We want to support different systems, and to also want to freely involve the offsets in the future. And however, the basic concept, right, the comparison of the offsets is still supported with the opaque offsets. The only things that makes difference is the arithmetic is no longer be supported. The arithmetic means that in the Kafka offset, because it's long, you can +1, +2. However, from the like use case perspective, like if a consumer want to resume from a position that's still supported, then if consumer want to start from next position, is also supported. It's the difference is it's the manipulate on offset is no longer allowed. So the conclusion is Northguard-Xinfra is a durable, virtualized PubSub layer for LinkedIn. We provide a solution for seamless migration from Kafka to Northguard. That's it.
Questions as usual.
Hey, Wesley, and congratulations. My question is, do you support in the Northguard world time-based rewind and forward?
Yes, we do support the API. Yeah, we do have API for time-based like seek. Essentially, Kafka, you can query the offset by timestamp. In Northguard, we can also query the offset by timestamp, but there is slightly different contract, but the basic semantic is supported. So what I mean is different contracts. What I mean is the accuracy. There might be a slight difference between Kafka and Northguard, and we don't like want to tie to a single system. In order, we try to look from the use case perspective.
Any more questions? One more here.
So you mentioned there are like millions of clients in the PubSub system.
Yeah.
And you're using MySQL to handle the traffic. Do you see any bottleneck on that?
So most of the request can be served from the cache because we don't have that like scale of the number of topics. Right? The number of topic it's so essentially the conductor has a cache that's like storing the topic metadata. So most of the time, the request is serving from the cache. The MySQL essentially used for two purposes. One is the topic metadata. The other is for the consumer trap points. We today don't see the bottleneck yet.
And to add to that, for the topic metadata part, MySQL or XMD will only be used during the bootstrap. So it's only in the metadata path, not in the data path. So once the clients are up and running, they don't have a dependency on the MySQL.
The committed offsets goes to MySQL.
Yes, that's right. So first, the commit rate is not that often, it's not that high, and we are not writing to MySQL immediately. So we have a couch-based caching layer, and we have code-less buffer, which means we only batch write into the MySQL as needed. So, and as for the metrics, we provision say 10x as the current Kafka offset commit rate. So we expect that to scale in next few years, and plus the APIs are pluggable. So if we see any bottlenecks, we can migrate.
So just out of curiosity, why not commit the offsets to a topic on Northguard? Just similar to in Kafka, consumer groups commit their offset as well to a topic?
So I think the main reason is because the clients now can work on top of more than one cluster, right? So if the topic is more dynamic.
Thank you.
So regarding one of the caveats you mentioned, right? Because the offset becomes like opaque, you cannot do +1, -1 thing, but you can still provide an interface saying, for example, .next or .add or .minus, and internally you can do the translation. Can you?
So we currently supporting .next. So there's API that's essentially consumer can can say I want to start with current position inclusively and also exclusively. This is next. Right.
Oh, okay. Thank you very much. Thank you, guys. Great presentation.
Right. Thanks to all of our speakers, to Ku, to Wesley, Pete, and Honor for the excellent talks. And thank you all the participants for joining us in person and remotely and making this event great. So we hope to see you again in 3 months in our next session. So thanks, everyone. Coming soon. Come to the next meetup.